a través del programa para profesores visitantes, que cada año es un programa que se puede aprovechar para poder invitar a profesores, dan pequeños cursos. Esta semana está dando un curso intensivo y poder discutir un poco con ustedes sobre todo lo que trabaja en esta temática. Fabio obtuvo su doctorado en el 2012. Él ahorita es investigador en la Universidad de Camerino, en Italia, y en esa misma universidad obtuvo su doctorado en el 2012. Después hizo varias estancias postdoctorales en el Sincrotrón Electra de Trieste, en Italia, en la Universidad de Manchester, en el Reino Unido, y en el Instituto Nacional de Vulcanología y Geofísica de Italia. Su principal línea de investigación es geoquímica, tecnología experimental, principalmente aplicando a constreñir las condiciones pre y eruptiva y durante la misma erupción en volcanes, desde trabajando recientemente en la erupción de La Palma en Canarias, volcanes de Chile y de Italia. Entonces, ahorita le va a presentar los resultados de experimento en 4D, principalmente en magma basálticos, para entender los procesos de movilidad de los magmas desde la corteza hacia el proceso de conducto previo a la erupción. Adelante.
Gracias. Thank you very much for inviting me here. What I'm going to talk is about what I have been doing in the last more or less 10 years. The title of this talk is In Situ for Decrystallization in Basaltic Magmas. Mostly I talk about crystallization kinetics and vesiculation kinetics in basaltic magmas, and with implication for magma mobility within the earth crust and fragmentation and eruptive style. So I'm mostly interested in magma chamber processes and conduit processes that control the eruptive style. So therefore, I'll focus my talk about magma vesiculation, degassing, outgassing, and magma crystallization during decompression, or simulating in some way conduit dynamics. Basaltic magmas are able to produce several types of eruption style. I'm very interested in this topic and how vesiculation, degassing, crystallization control the magma rheology during ascent, and how this control magma eruptive style. So basaltic volcanoes can erupt, as I said, with different style, less frequently like highly explosive eruption, more frequently like strombolian or lava fountaining or lava flows. How this magma, that usually is low viscosity magma, can promote this wide range of eruption is still debated and a very fascinating question, scientific question. So what I'm doing and what I have done in my career, I started with performing experiments in the lab with ex situ view. So it means that I cook my rock and then I quench and then I look using microprobe, using SEM, microscope, and so on, always looking the textures in 2D. What I wanted to do during my PhD is to move from 2D to 3D. And then I thought, okay, I can look my data, my experiments, the results of my experiments using X-ray computed tomography. And here I report just, I'll do a brief introduction of X-ray computed tomography, because at the end, what I wanted to do is to combine X-ray computed tomography with experiments in order to record processes in real time, in some way simulating magma chamber processes or conduit processes, recording the processes like crystallization and vesiculation in real time. And here I reported just a picture of Sir Godfrey Hansfield, that was one of the pioneers of X-ray computed tomography, and in the 1975 got the Nobel Prize in physiology and medicine for introducing the first computed X-ray tomography. And he said that it cannot be an exaggeration to maintain that no other method with X-ray diagnostic has during such a short period of time led to such remarkable advances with regard to research and number of applications as computer-assisted tomography. So therefore, with this technique today, we are able to scan dinosaurs, entire dinosaurs, or tiny crystals that grow into magmas. So, and I use this technique in order to do so. How it works, X-ray computed tomography. I'll do just a brief introduction, and then I'll move towards the experiments. Just principle about X-ray computed tomography. You have to imagine that this is our sample, is a rock with different phases, and you have an X-ray beam that will pass through the sample, and the phases, depending on the density, will attenuate the beam. So therefore, at the end of the going out from the sample, we will have an attenuated beam that will be then recorded by a camera that has the possibility, the capability to transform X-ray beam in light, and so taking picture over a certain range of degree. Basically, what we can do is to reconstruct our sample with several images over a certain 180 degree or 360 degree, depends which kind of acquisition we want to do. And basically, we will have a collection of images that through algorithm we can put together and have our rock directly. We can visualize our rock directly in 3D. So this how it works in a simple way. And then we have two different conventional X-ray sources. One is the lab one. One example you have also here. These are, you have the source here, the sample here. The sample is located in the rotation stage, and you have the camera here that will record images, and then you can reconstruct your sample in 3D. Usually, these conventional sources have the beam that is conic. I'm not sure what you have here. Possibly the new generation have a parallel or nearly parallel beam. This will help, and then I'll show you with reconstruction and to obtain very high quality data. And the synchrotron instead, we have a parallel beam. So therefore, what we can play with phase contrast much more than a conventional source that have a conic beam. And this, I'll show you the importance of phase contrast for magmatic and to study textures and rocks later. And here, what you have is just the entrance, the synchrotron. It's, are you familiar with synchrotron? A bit. It's the it's a ring where electrons will be accelerated, and then you produce X-ray, and the X-ray will be used for different technique. X-ray tomography is one of those. And the X-ray beam will enter into the experimental arch. Here you have the sample and the rotation stage, and here the camera. Okay. So the good thing for parallel beam is that we don't need correction of the shapes at the end. So therefore, using synchrotron radiation is very powerful because we can reconstruct without having a post-processing algorithm that will modify too much the shape of your object, of your phases. And then the other thing is that for my purpose, so to perform experiments in 4D, X-ray tomography at synchrotron is really important because the beam is more energetic, you have more flux, and so therefore you can perform real-time experiments. It is more difficult with this kind of source, the conventional source. So basically, And what we have a sample that rotates over 180 degrees or 360. This is the X-ray beam that will pass through the sample, will be attenuated. We will reach this camera. The scintillator screen will transform the X-ray beam, so the attenuated beam, in light. And then this is a camera. This works like a normal camera. We record images in grayscale from white to dark, so from white to black. White means that the phases are really dense, like in our case in rocks can be oxides. Black can be a void, like a bubble in a volcanic rock. And then there are algorithms that will reconstruct the projection of the images obtained, and we can reconstruct our object directly in 3D. So one important thing is this: having a parallel beam, I can play with the distance between the sample and the detector. Okay, so this distance is really important, particularly when we talk about rocks, because we can change the phase contrast. We can enhance the contrast among phases, and particularly if we talk about glass and feldspar, that where the density is quite similar. Very often, if we don't play with this distance, we will obtain just a gray object where we cannot see the phases. So therefore, what we have, if we have the sample very close to the detector, we will work in absorption mode, where basically we cannot enhance any difference in in contrast. Instead, if we increase this distance between the sample and the detector, basically we can increase the contrast. At the end, what you can obtain is just this: a mimosa flower obtained in absorption mode, and here you can see a mimosa flower in phase contrast mode. So you can see more details, and this can be applied in, for instance, just to understand, this is a metal alloy acquired in absorption mode. Here is a just gray matrix. Then if we use phase contrast, we can see lamelle that this is the same sample acquired in two different ways. So therefore, this phase contrast that was introduced in 1998 from the ESRF synchrotron, the group in Grenoble, it's really powerful, particularly in rocks, because what I did then when I was in Trieste is to apply these algorithms and other algorithms to like phase retrieval that was used just in biology to study cancers, where you have tissues with very similar density. I wanted to apply these algorithms to rocks. And at the end, the result is that if you start from an image like that, where there is a completely lack of contrast, here we have trachytic magma with K-feldspar acquired in absorption mode. You cannot see anything. If you use phase contrast plus phase retrieval, so plus algorithms that will enhance the contrast, you start to see the glass, K-feldspar, oxides. So that's really powerful. At the end of the day, what you can get is this. This is scoria from Stromboli, and then enhancing the contrast among phases, you can separate glass with the crystals inside. These crystals are just inside here, and you can extract them and quantify directly in 3D. So therefore, I wanted to move from 2D approach to this approach. This is just static. So you have a piece of rock, you scan, and you see what which phases you have inside. And I did the same for experimental samples. These are spherulites that I produced during experiments with my trachytic magma, and I produced these spherulites, and then I was able to separate the lamelle and study the crystal growth and so on. So mostly I performed analysis at the electrosynchrotron Trieste in Italy, a Swiss light source. I'll show you something later. and then a demo light source during the last 8 years. Particularly, I worked with Rafael a lot between 2017 and 2019. And then, and what we developed was then to move from static 3D to perform the experiments and recording crystallization in real time. We developed initially a furnace at this furnace is ambient pressure, very high temperature. We can reach 1200 degrees Celsius, so we can study basalt, basically. Here you have the heating elements. Here, this is half of the furnace. There is another, exactly another part similar to this that will be attached here. And then you have the 2 thermocouples that control the temperature precisely with an error within 5 degrees Celsius. And the sample is located here. So basically, you have this rotation stage, and here you have the sample. So it's located exactly here. And the sample is contained within an alumina crucible. So basically, you have an alumina crucible, and then inside we put a glassy basalt as a starting material. Okay, and then what we did is, since this furnace, you cannot have pressure, is just a furnace at ambient temperature, what we developed this crucible with these pistons in order to pressurize our melt. So here you see this is a broken crucible where the basaltic melt came out. So we were able to pressurize our system with particularly using anhydrous glass. Okay, so we can simulate a magma with volatiles dissolved in it at pressure, and magmatic pressure and magmatic temperature. So here, I have the pointer and doesn't. Okay. How do I remove the pointer? Screen pointer. Okay, the arrow. Okay. There. Okay. This is basically a diamond-like source arch where our experimental apparatus is. Here, where the beam will enter, we pass here. This is our experimental apparatus. Okay, this is the furnace. The beam will pass through this window. I forgot to mention that this furnace has 2 windows in order that the beam will pass through. And then this is the camera. So between our sample and the camera, there are 2 meters. So we played a lot with the distance between the sample and the detector in order to enhance the contrast and to enhance the phase contrast among phases. Okay, and we performed several experiments with this approach. Now I'm going to show you a bit more science and related to basaltic magmas and crystallization. The first topic that I'll discuss will be magma mobility within the crust, and the second one, fragmentation in basaltic magma and the highly explosive eruption. So regarding the first topic, the observation is, this is a dike in Etna volcano. So this dike, if you look the textures in the middle of the dike, you observe this kind of textures where you have irregular crystals. And then if you move from the core of the dike towards the rim, the crystal shape will change completely, and you observe this anhedral dendritic crystallization. So, and was estimated by previous works that this transition was more or less around 10 megapascal. So therefore, what we wanted to do is our scientific question was how crystallization will control magma mobility within a dike. So, and another important aspect to consider is that crystals shapes evolve decreasing temperature and increasing undercooling. Okay, and what is undercooling? Undercooling, I explained this morning during the course. So just to make it simple as a concept, we have pressure, we have temperature. This is the liquidus line of a pyroxene, for instance, okay, in your basalt. Under water saturated condition, so your basalt is full of water for each pressure. So above this line, no crystallization. So you stabilize, just melt. Okay, your magma is liquid. If you move at this condition, a subliquidus condition, crystallization will be promoted. So, and the undercooling is the difference between the liquidus temperature and the temperature at which your magma is. Okay, so therefore this difference is driving force of crystallization and will control crystal shapes and crystal kinetics. How do you impose undercooling? Through cooling at a constant pressure, through decompression at constant temperature, or during ascent, both cooling and decompression can occur together, and your system can move from a super liquidus condition to a subliquidus condition. So where crystallization can be promoted. Okay, our experiments in 4D, we fixed the pressure at 10 megapascal in order to simulate the Etna dike. And then we started at a temperature of 1210 degrees Celsius, so above the liquidus, no crystallization. And then we moved our condition at 1150, so imposing 10 degrees of undercooling. And then again, after 1 hour and a half or 2 hours, I don't remember, we decreased the temperature at 1130, increasing the undercooling at 30 degrees Celsius. So here you see a picture in 2D. This is the initial condition above the liquidus, then the first step at 1150, and then when you see this dendritic crystallization that occurs, we are in the last condition. So this is just a video of our experiments in 2D, but we go to see how crystals are, particularly cyanopyroxene, are at a different condition. The first three figures are at undercooling 10, so 1150 degrees Celsius. So this means that this is the minutes after the nucleation occurred, the first nucleation occurred, and you track the evolution of crystals through time. So 31 minutes, 51 minutes, 71 minutes. You see that new nuclei will form and crystal grow, and they grow with a hydral shape, well formed. They are prismatic. And then after 90 minutes, we decrease the temperature at 1130. And so therefore we increase the undercooling at 30 degrees Celsius. What you observe that from 91st minute to the 131st minute, you have a massive growth of cyanopyroxene. So kinetics will be much faster, and particularly the shapes are completely different. So you have this skeletal dendritic shape controlled by the undercooling, and the kinetics are much faster than this condition here. So here you can observe the experiments through time. So before we recorded a magma crystallizing through time in a couple of hours. So this is a summary of a couple of hours of crystallization, more or less. And here I reported just the evolution of single crystal. I isolated one single crystal in order to observe this shift. And you can appreciate when we move from 10 degrees of undercooling to 30 degrees of undercooling. So you have a much more elongated crystal. So your aspect ratio, the aspect ratio of the crystal is increasing really fast with the rapid kinetics, forming this dendritic growth. Okay, we quantified the kinetics of all the phases. Here I reported just one, and you can follow the length of the crystal through time at under cooling 10, where the growth is controlled by interface. So therefore, it means that diffusion is much faster than growth. Growth is not so fast. And so this is the evolution of this crystal here through time. Okay. Then when we move to under cooling 30, this dendritic overgrowth will be formed. This spiky along from the corner of the pyroxene will be formed. This is because you have basically a boundary layer with enriched of incompatible elements around the erythral shape. So therefore, the dendritic shape wants to find the nutrients, the elements good for the pyroxene far away from this boundary layer that is close to the initial shape, and the growth will be developed in this direction much faster, and it will be limited by diffusion. The diffusion will be the growth is much faster than diffusion, and you can see the length of each branches through time is representative. The blue one, the branches here, and the red one are the branches in this. The blue are this, the red are this, and you can see that the growth is much faster. And you can observe also here, this is the growth rate versus time, and this is the growth rate of the wither at 10 degrees of undercooling, and this is the growth rate of the branches that are formed when the growth is limited by diffusion, okay, at higher undercooling. So another observation here is that I reported just 5 crystals within the sample, and well, you can observe that this is the first erythral crystal formed through time, so it's forming here. From here to here means that we have an incubation time where crystals are not able to form, despite we are at an undercooling condition. So it means that nucleation is not an instantaneous process when the system goes from superheating condition above the liquidus to undercooling condition below the liquidus. And then you have this first peak. So this nucleus grow in this way, but then you continue to have nucleation events through time, and after like 75 minutes, you have another nucleation event, and the growth rate and the profile of the growth rate is exactly the same. So the 4 crystals that form at the end of this process can have the same shape of the crystal that were able to grow at the beginning. Okay. This is the first observation. The second observation that all the dendritic branches have more or less 1 order of magnitude is 1 order of magnitude faster than more or less than the erythral crystals controlled by diffusion control growth. So this means that the shape of the crystal is much more elongated, and here you can see I reported the aspect ratio through time at undercooling 10 and undercooling 30. So the aspect ratio of our erythral crystal, considering the length of the crystals versus the short axis of the crystal, is more or less around 4, and it is constant through the experiment. As soon as I decrease the temperature and increase the undercooling, the aspect ratio, of course, increases because the growth is promoted just in one direction along the z-axis. So, and this, if you look at this, and we put together with the crystal fraction and the maximum packing fraction. So the crystal fraction will increase, the maximum fraction will decrease at the under cooling 30. So it means that the crystal fraction and the maximum packing fraction will be closer to each other. So we are going to modify the rheology of magma. And then if we calculate the ratio between the crystal fraction and maximum packing fraction through time, we can see that we are going towards non-Newtonian rheology. Okay, and also if you can calculate the flow index, that I don't want to go in detail about these kind of things, but it's just an index to quantify and to monitor the evolution of the rheology of your melt. So basically, you go from a Newtonian behavior to shear thinning behavior, so non-Newtonian behavior. So it means that just a cooling of 20 degrees Celsius, increasing the undercooling from 10 to 30, can modify dramatically crystallization kinetics and crystal shape, and this will have effect on magma rheology. So we put all this information into a dike propagation model. What we wanted to simulate, this propagation of a basaltic dike within the crust with 3 scenarios. The aspect ratio constant 4, so despite undercooling will increase, kinetics will not change, so we have a constant aspect ratio during ascent. Then we consider the aspect ratio maximum considering our experiments and other experiments performed on basalt. And so therefore considering the approach to equilibrium really fast, so therefore we reach the maximum aspect ratio possible in the shortest time. And the aspect ratio minimum, that means that the disequilibrium takes longer, and so therefore our basalt is not able to reach equilibrium, so crystallization is not able to reach equilibrium quickly. So we have the red line, the red line is the maximum, the blue line is the minimum, and the black one is just constant aspect ratio. So what we see that during ascent, here we simulated an ascent from 10 kilometers to the surface, and the question was how crystallization will affect magma ascent within the conduit. So therefore we see that here the aspect ratio for the black is constant during ascent. For the red one, when crystallization will be promoted, will increase really fast because the approach to equilibrium is really fast. So the blue line, we have an approach to equilibrium that is lower. In terms of maximum packing fraction, so when the crystal fraction will meet the maximum packing fraction, means that you have a solid rock. So the magma is not able to move anymore. So we have this situation with the red line at 500 meters below the surface, because the red line represents the really fast evolution of the aspect ratio. If we consider the blue line, we will meet the maximum packing fraction right at the surface. So it means that this dike maybe potentially can reach the surface and feed an eruption. For sure, if we consider the maximum packing fraction constant at 4, so a withdrawal shape all the time, not influenced by the kinetics, undercooling, and so on, this dike will reach the surface and will feed an eruption for sure. So therefore, what we are showing here, that the crystallization controlled by undercooling and kinetics can affect the mobility of a dike, of basaltic dike at depth. So just to summarize the results of this, so we integrated 4D experiments with the dike propagation model, and these show that we have a transition between two crystallization regimes, from interface control growth to diffusion limited growth, with a very narrow range of temperature from 10 to 30 degree of undercooling, basically. And we have, so this means that the modest cooling of the system can increase undercooling enough to promote dendritic or skeletal growth. So this means that the aspect ratio will be, so the growth will be promoted along one direction. And this will promote a transition from Newtonian to non-Newtonian rheological behavior. And so this will affect magma mobility, potentially freezing magma in a dike or in a reservoir in a few hours. So, and this has a strong implication about if a dike can reach the surface or not. Now, if a magma is able to reach the surface feeding an eruption, what we observed during 10,000 of simulation with the basaltic magma, considering disequilibrium in crystallization and vesiculation during magma ascent, that the compression rate and viscosity control the eruptive style. So the compression, very slow decompression rate, the blue one will promote a fusive eruption with basaltic magma. If we have a faster decompression rate, we can associate with ascent rate in some way. So we can promote highly explosive eruption, the red one. So it means Plinian eruption. If we have a very fast ascent rate, we can promote high fountaining activity. And this is correlated with the viscosity. So the high ascent rates means that fast decompression rates means that crystallization kinetics has no time to form crystals because disequilibrium, because the approach to equilibrium maybe is too slow. And so therefore the viscosity remains low because you don't have, your magma will be liquid. And so therefore fountaining will be promoted compared to highly explosive eruption where you have the right ascent rates and fast kinetics, fast crystallization kinetics. This will increase viscosity high enough, around 10 to the 6 or 10 to the 7 Pascal second, where fragmentation can occur, feeding Plinian eruption. If the crystallization will be promoted too much because the ascent is too slow, so therefore this basaltic magma can reach equilibrium, means that will be highly crystallized, and highly crystallized means high viscosity, and so therefore will be difficult to feed explosive eruption, but instead we will have fusive ones. So based on this information about the model, what we wanted to investigate how, particularly how crystallization control the magma rheology during ascent, during fast decompression rates and fast ascent rates. So we consider several highly explosive eruptions on Earth that in basaltic system. So we know a few of them. We know the 122 before BC Etna basaltic Plinian eruption that produced a Plinian eruption that destroyed Catania in the Roman period. Then we have the Masaya basaltic Plinian eruption in Nicaragua, the Fontana Lapide and Triple Layer. This system is able to produce several pools of Plinian eruption, and the last one that we considered was the Tarawera basaltic eruption, the Plinian eruption in New Zealand. So if we observe the textures in basaltic Plinian eruption products, we observe very rich in macrolites. This is the glass, these are plagioclase, and then we observe tiny pyroxene that can grow, that can nucleate heterogeneously on plagioclase, with these plagioclase that have these skeletal shapes. I can show you other example here. So this is the plagioclase, this is the pyroxene. this heterogeneous liquidation of pyroxene on plagioclase, and this with the swallow-tailed shapes that are related to high undercooling. So these shapes are usually related to high undercooling. Oops.
The starting point, a natural salt.
Yes.
Melt.
Yes.
Are you able to reproduce the original textures when you do the
I'm going to show now.
Oh, sorry.
That was just interrupted.
I have a question more technically about the experiments compared with the emulation of what really happens in nature. In what I understand, in your experiment, you compress or how you put the pressure in the sample? It's an axial pressure?
Yes.
Okay, so how that emulate what's going on in
Because
the
the
subsurface?
piston basically sealed the crucible, pressurizing it, and then our glass, our starting glass, has water dissolved in it. Okay. When you heat up, basically, if the water will be not dissolved, so it means that it is dissolved into it, and if it's the pressure, okay. So what we did is to just reach 10 megapascal. Was just we know that this basalt with 1% of water is saturated at 10 megapascal. So what we did at the beginning, the piston was at higher pressure, pressurizing our sample. We released a little bit the pressure with the piston up to see the first bubble appearing. So it means that is the solubility at 10 megapascal, and we kept our piston pressurized like that for the entire experiment.
Yeah, and the temperature, how did you put the temperature? There is a gradient of temperature because you put two thermocouples, and then I couldn't understand really how, because the gradient of temperature, if you have a gradient of temperature, it also affects your experiment.
Yeah, we have a gradient of temperature, but not within the part of the sample that we observe. So we have 5 millimeter area where the temperature is constant, and then above and below, of course, will decrease. But our sample is located exactly in the hot spots.
And the slice that you have, the topographic slice, is just in this, those 5 millimeters.
Yeah, exactly.
Exactly. And how often do you get the 3D image?
Every 1 minute.
Every 1 minute?
Yes, of course, I showed volume every 20 minutes because oh, okay. So to come to your question, that was a good question. How if we reproduce the textures? Okay.
Silenzia tu macchina.
Okay, so these textures indicates high undercooling in our system. So for this, the first step, we know that high undercooling should be something that controls this kind of crystallization. Then we have, we know that highly explosive eruption are linked in some way with fast magma ascent. So the question is, this high undercooling can promote a really fast crystallization time to change the rheology, or fast magma ascent is too fast to promote crystallization. Which one is faster, crystallization or magma ascent? This is the question. And so therefore, this has strong implication about fragmentation, because if crystallization is fast, you can change rheology, and during fast magma ascent, basically you can promote magma fragmentation, and so therefore highly explosive eruption. Otherwise, no. So therefore, this was our scientific question. So therefore, we start from a magma that was partially crystallized with this pyroxene and oxide. This is a pocket of melt. Okay, it's a pure melt here in the middle, and then we imposed during these experiments a very fast cooling, 0.4 degrees per second, so it means 24 degrees per minute, and this simulating a fast perturbation of undercooling. So what we want to simulate is a fast perturbation of undercooling, cooling down our system quickly. And so you see from time 114 seconds to time 294 seconds, so more or less 3 minutes, you can observe plagioclase and dendritic pyroxene growing around them. After other 3 minutes, is completely crystallized. So therefore, when the system is perturbated fast, so the undercooling is increased fast, crystallization can react fast. And this is what we observed in 3D. So we produce this swallowtail plagioclase. This is the experiment, natural Etna. Okay. Of course, our system went too ahead with the undercooling. We investigated undercooling between 80 and 175 degrees Celsius. We produced this skeletal plagioclase with this dendritic pyroxene around them. So here in the natural case, you have this skeletal plagioclase and then this initial dendritic crystallization of pyroxene, but then you have the rest is melt. So it means that in the natural case, the natural magma didn't experience very extreme undercooling conditions. So we put all this kinetics data into a model that we developed in 2016, where basically we can simulate magma ascent, basaltic magma ascent within the conduit, considering the strain rate criterion introduced by Capale in 1999 for magma fragmentation. And basically, we simulated we simulated the conduit dynamics of 1 to 2 BC Etna eruption, considering two here characteristic time means that we have two kinetics. One is fast, one is slow. So it means here with the blue line, crystallization is really fast, considering our experiments. It means that the equilibrium is reached quite fast. Instead, for the red line, we used a very slow crystallization kinetics that simulates an approaching to equilibrium very slow. So, and here we start from 6 kilometers, simulating a magma chamber 6 kilometers, and then investigating conduit dynamics. And here we tracked the evolution of undercooling during ascent. Here you see the crystal content during ascent, considering the fast crystallization and slow crystallization. As you can see, when the system approach equilibrium really quickly, the crystal content, plagioclase pyroxene, can increase quite fast in the last 3 kilometers, reach this point. This discontinuity is related to this discontinuity here, and is related to magma viscosity. Is when you have this discontinuity, means that the model is showing a transition in rheological behavior. This is the fragmentation level, and this was induced by a really fast viscosity, magma viscosity increase, because crystallization is highly promoted in the last 3 kilometers, up to reach 10 to the 6 Pascal second. So basically reaching a threshold where during fast magma ascent, and the fast magma ascent means that the ascent rate increased from 5 meters per second to 15 meters per second. The last part, when you reach 10 to the 6 Pascal second, basically basaltic magma can fragment. So feeding highly explosive eruption. In this case, instead, the red curve showing a very small amount of crystallization during ascent, because the equilibrium is approached slowly. You have yes, an increase of viscosity, but not too much, and this will feed, basically will reach the surface, but feeding possibly fountaining eruption. So another aspect that is important to consider, that highly explosive eruption are also promoted when the initial temperature in the magma chamber is cooling down compared to other activity like the high fountaining. So basically here you have the frequency of solution. Here we have more than 10,000 simulation in different conditions. And here is reported the initial temperature, considering whatever we said before, but just look at the initial temperature. And so when the temperature is quite high, high fountain will be promoted, because at high temperature, you reduce the undercooling, and so you slow down crystallization. If you start from a magma that is cooled down, so it means that it's cold in the magma chamber, so you start already a condition that the undercooling is quite high, so promoting fast crystallization during the ascent. In fact, the frequency of solution for explosive eruption at lower temperature is quite high. This is important information for monitoring, for instance. Another aspect that is important is the amount of crystals at the beginning, and like phenocrysts. So therefore, if the higher the amount of phenocrysts at the beginning, the higher will be the possibility to have a highly explosive eruption. We have the reverse behavior with high fountaining. Just to highlight this, we investigated the highly explosive eruption in the Masaya volcanic system in Nicaragua, and what we observed is that all the products have crystal mash remobilized in the magma chamber, so confirming that that chamber was cooling down and then probably was reactivated, and so you are mobilizing basically a cold mash, and then you have magma that was already partially cold, and then triggering the eruption, and so the conduit dynamics works exactly what I said before, with the same dynamics. And just to summarize about fragmentation in basaltic magmas, so we performed these in situ experiments where we perturbated the system quickly, so we perturbated the undercooling quite quickly, and and we obtained basically magma fragmentation where the magma, the initial temperature of the magma was lower than 1100 degrees Celsius, undercooling between 80 and 175 degrees Celsius, fast ascent rate at the bottom, close to the magma chamber, 5 meters per second, up to 50 meters per second in the top part, and syn-eruptive crystal content higher than 50 volume% was produced by fast crystallization during ascent, and magma viscosity around 10 to the 6 Pascal second where fragmentation can occur. So I conclude this first part just comparing the two kinetics for conduit dynamics and very fast magma ascent, where fragmentation, where rapid crystallization can occur due to the fast perturbation, and then fragmentation is promoted and therefore highly explosive eruption. So this will be mostly promoted by this large perturbation of undercooling. When we have a slower perturbation of undercooling with a small change in undercooling, this can promote instead the dendritic crystallization that can affect magma mobility during slower magma ascent. And this will control the propagation of the dike from deeper depth to the surface, if it's able to feed an eruption or not. As the last part, I want to introduce something that I'm doing at the moment, that we want to investigate also vesiculation and bubble growth during ascent. So far, I discussed just magma crystallization. So, and to do so, we need to decompress the system. This is the first experiment that was performed in 2012. This is a pioneeristic experiment performed by Don Becker at Sweet Light Source in Switzerland, where he used basically an hydrous glass. This is a basaltic glass hydrous with the 3% of water inside at ambient pressure, just heating up this glass with a laser and recording in real time. So therefore, the vesiculation that you see, it's quite fast. It's within 18 seconds. This video is just 10 seconds. And basically, heating up above the glass transition, you obtain this kind of scoria. Okay, this was the first experiments investigating vesiculation in real time at ambient pressure, just heating. Then with Rafael, as I remember, we performed during the night. We played with the piston that I introduced before. And then this is a basaltic magma. And we played and we removed the piston and we increased the pressure with the piston, basically decompressing and recompressing the system in order to investigate the coalescence of bubbles and how fast bubbles can coalesce. This is an important aspect because during magma ascent, coalescence of bubble can determine if the system is degassing, but still the bubbles will be coupled with magma, so therefore you don't have outgassing, and this will maintain a lot of energy during ascent, will accelerate the magma ascent, compare if you developed a network where then at the end the permeability will be dominating the gas permeability will be developed basically, and the conductivity. This will determine basically outgassing and possibly decoupling between gas and magma. So these experiments were performed with this idea. And so we performed this. You can see the evolution of bubbles through time. This is a few seconds from the beginning to the end. It's 20 seconds more or less. The difficulty was to control pressure with the piston. So therefore, moving up and down the piston, we produced some decompression, but we were not able to track exactly what the pressure was imposed. So therefore, the idea was to develop an internally pressured vessel where the system is, so you can compress and decompress your system with gas. So you can control precisely the pressure inside of your system. So basically, this is an internally pressured vessel. So the sample is inside. Here we have two windows, one here, one on the other side, in order that the beam will pass through. And we developed initially a crucible to perform, in this case, radiography and not tomography. because as I said before, tomography needs that the sample will rotate. We don't have at the moment this system that is able to rotate internally. So therefore, the sample is fixed inside and we can take just fast images through time. So therefore, we will have 2D images through time during the compression. And so this is the internally pressure vessel in the beamline at the diamond light source. This is the camera, this is the system, and this is the pressure control and the temperature controller. And so, yes, I'll show you this. These are the two images through time. So this is the time from 0 to 14 seconds. And basically what we wanted to observe is how fast two bubbles touching each other can coalesce and recover their shape. So it means that from here to here, two bubbles are connected and still connected here, and then they close and they recover their time, their shape. So this means that during this part, more bubbles can be connected, so therefore a permeability can be developed, so a connectivity can be developed. So it means that outgassing can be promoted, so decoupling between gas and magma. If this recovery is fast, it means that the system can close again quickly, and so therefore outgassing will be not promoted. So I think this is the last, yes, the last slide. So we were able to measure bubble growth, bubble coalescence, recovery time, and where a permeability network can be promoted and the outgassing. And we observed during our experiments that up to basically 4 megapascal, 4 megapascal, the system was completely closed, and despite you have coalescence, the coalescence is so fast that permeability is not developed, and you have a coupled system with so your gas is coupled with the magma. After 4 megapascal, basically we can observe a very the recovery time increase, and the velocity during gas increase. So therefore, after 4 megapascal, we think that basaltic magma can develop permeability, and so therefore promote outgassing and decoupling between gas and magma. These are preliminary results that are under review in Science Advances. And I wanted to thank you for inviting me here.
Your starting point is a result that you felt.
Yeah.
The first part.
Yeah.
But that sample is already the gas. So you're melting and crystallizing a magma that is definitely poor in gases.
So in the first example that so when we prepare our glasses, we prepare our glasses in furnaces at high pressure, high temperature, like PZM or internally pressured vessel, that is not this one. So therefore we prepare our glasses that are hydrous inside with different amount of water.
Glass, basaltic glass.
Yeah.
That's the starting point.
Yeah.
Basalt.
Yeah.
It's glass.
Yeah.
It's hydrated.
Is hydrated, yes, exactly. With usually we put 0.5, 1, 2% of water. And so therefore our starting material is already hydrous at the beginning. And then if you apply pressure, enough pressure and temperature with the system that I showed you before, basically you can keep your volatiles dissolved in it, and then you can play with temperature, having basically an hydrous basalt. So the picture that I show you here, so here we were able to basically to keep the volatiles dissolved, and not here. This is was remove the piston, and so therefore you see that the bubbles with the water with salt. Then we pressurize again, and we put the liquid, the water, be soluble again with the melt, and then we decreased again. So we played like this to show that we were starting from an anhydrous glass, so an anhydrous melt, and then you can play with pressure or temperature.
And your question is surprising. So by 1,000 degrees, the sample is already crystallized.
1,000. Yes, yeah. So basaltic, yeah. So
That's really
I don't know which one you refer to, but I can show you here. Maybe it's yeah. For instance, the cyanopyroxene liquidus is here. So before 10 megapascal, already 1100. So the plastic is more or less here. So it's a lower temperature. Then depends which condition you are. So how much water. If you increase the water, this will shift a lower temperature. If you make it anhydrous, it will be a higher temperature. It depends on the conditions. Yeah, but 1,000 for sure it can be completely crystalline, or almost. Thank you.
Bueno, muchas gracias. Nos da todos los días, así que